All right. Good Monday, everybody. Welcome to another episode. I'm here again with Dr. Craig Wright, the inventor of Bitcoin. And what are we going to learn today, Doctor?
Okay, so I'm going to have a quick segue and just explain something, and then I'm going to start going on what we call number 42 and detail that. Now, many years ago, I noted that Bitcoin is sort of a system that ends up in data centers and all this sort of stuff, and people keep thinking about, oh, well, what about me? Well, compete. I mean, I'm sick of that argument personally. The what about me one? Life's not fair. Equality is not fair. Get over it. If you want to try and build a node and you want to be part of it, good. But raise money, do it properly. There's no place in Bitcoin for Raspberry Pis. It's not a system for home users running in mum's basement. And if you don't like that, too bad. The trade-off is, do you have a small system that a few geeks get to use, that all use Raspberry Pis, or do you have a large system with a few static commercialized sort of nodes that allows the sort of financial inclusion of billions of people globally? One or the other. And I don't want to make a small cypherpunk experiment. I never did. I want to make a system that allows for monetary inclusion, that allows people who are those ones that BTC don't seem to want, you know, the ones that earn less than $1 a day, Tuvalu, etc., to be able to interact and be part of a global economy. And if people don't like that, then I don't really care, because that's what I'm building. Go build your own.
Okay.
I mean, so the simple answer about all these, it's not fair that nodes do X, Y, Z, and the other. Of course it's fair. It's in the rules. Now, when sort of AlphaGo a few years ago beat a human player in chess, people said, that's an alien move. It's nothing that a human would ever do, blah, blah, blah. Guess what? It's fair. It's in the rules. No one thought of it. The computer sort of discovered a combination that allowed it sort of a win. Humans now integrate that and do it. But the fact of the matter is there was an unexpected random sort of hop that actually follows the rules and no human would have thought of in a long time. That's how systems work. If people find ways of exploiting existing areas that are valid, good. Sitting there going, it's not fair, these guys are getting paid to transmit transactions, but I don't want to do them because the relay fee is too low, then do the same thing yourself. Take 1 million transactions in and see if anyone else wants to transmit them. If they don't, then that will end up being a cost. So anyway, side note there, and to get on to reality here, I'm going to start you on a number of white papers, some of which have been granted and things like this. So I'm going to start you, first of all, on old number 42. Now, this is the elliptic curve sort of Diffie-Hellman methodology, where what we're doing is creating a shared key between different parties. Now, don't worry, I'm not saying that I invented Diffie-Hellman. If you have the slightest inkling of how patents or academic papers work, like when you do a thesis, for instance, you do a literature review.
Yes.
And in a literature review, you're not saying that these are your ideas. There's a similar aspect of a patent, which is prior art. So if you want your patent to get through, you need to put down prior art. So what you do is you say, elliptic curve cryptography, invented by these guys. Diffie-Hellman, invented by Diffie and Hellman. Yeah, and you go over and you say, these are the things that already exist. This is how they're being used at present. Now, that is all fine and good, but the nature of how people utilized public-private key pairs in Bitcoin, in systems before Bitcoin, such as PGP, was you get one key and you sit on it.
Mm-hmm.
and you sit on it forever. And
Yeah.
unfortunately, the adoption of Bitcoin by the cypherpunk sort of brain dead zombie crew has led to
Okay.
this integration of an idea that isn't Bitcoin. They've ignored where I've stated, do not reuse keys. And what do you see? They put their Twitter address up on their website, or they put it up on their Twitter
QR
site.
code.
They put their address. They put it.
Mm-hmm.
So basically, they just pump out this thing that you keep sending to, and everyone's the same. Now, there are a variety of what we call 42 methods. The simplest one is what I've talked to you about before, which is doing a Diffie-Hellman secret
Mm-hmm.
between two parties, where now you can make a new key for both pairs.
Mm-hmm. Yeah.
This could even be made more complex by, instead of using a message digest such as SHA or something like this, you can put a HMAC in there. Now, with a HMAC, you can add extra information, whether it's public or not, such as like invoice numbers or ordering numbers, etc.
Mm-hmm.
So, as my key, it could be a known variable that updates every now and again, and I could have invoice 1, invoice 2, invoice 3, invoice 4, etc. in a standard format. And each of that will give me a new value.
Mm-hmm.
So that allows me now to exchange with you without actually doing an exchange, because I know your official out there published public key, for instance. It can be a government certified one that links to your tax. Okay, so you keep that private. It's on a smart card. You do all the things to protect it. You don't let it go out to be stolen because it's only that single thing, and you never use it as a Bitcoin address.
Mm-hmm.
So
Yeah, you always
no,
derive new keys from it.
yeah. So there's no sort of conflict sort of attacks where the K value hasn't been generated randomly or anything like this, because you're not using it publicly. If you never sign with it, there's never a K value attack. The Sony incident where they had break-in, that was because they didn't have their random numbers generated properly. We don't have that issue if we never reuse keys. So now that we've done that, I can do something like issuing you a purchase order, or you can issue me a invoice number, or anything really that we use. It could be the Unix timestamp.
Mm-hmm.
I don't really care. We can negotiate any value. And simultaneously, I can calculate what that key is. You can calculate what that key is.
Mm-hmm. Then we have a
No
shared
problem.
secret. Yeah.
Exactly. So here's the magic of ECDSA. If I have my shared secret plus a
Master.
secret that I keep myself,
Mm-hmm.
you don't know what my secret is. It gives you no information.
No. Mm-hmm.
So I can now create a new key. So I can put my public key out there on my website publicly. And even if you're offline, I can send you money.
Mm-hmm.
Because I can send it, like text you later, or give you something that is the number for where you've been paid.
Mm-hmm.
And you know my key, you know your own key. Now you can calculate the new key, because ECDSA is homomorphically additive.
Yes. Mm-hmm.
So your key plus this key equals new key, and you can calculate all that. And you can grab the Bitcoin in there and use it.
Okay.
It's a rather difficult process, isn't it? I mean, when you think about it, you now have a set of automated updates But it's got this, oh, but what if someone sends me dust? Well,
Okay.
no one will be sending you dust because you won't be reusing those addresses.
Mm-hmm.
No one will be doing I mean, dust is used, of course, to try and get people to stupidly attach it to other transactions and pile them together so that we can now go, ha, this is
Okay.
connected to that, like cookies. I mean, dust is really used like cookies.
Mm-hmm.
But what if instead we had hundreds of thousands of addresses per person, all related to different things, and we just don't amalgamate them?
Mm-hmm.
And
Yeah.
we don't amalgamate the dust. And we keep having everything all over the place. Makes it a bit more difficult, doesn't it?
Mm-hmm. Yeah, it seems like not a huge challenge, I would say. Just don't
Mm.
use if somebody's send me dust,
Hmm.
I just forget about it. I
So,
don't use it. Yes.
what language are you playing with at the moment most?
Uh, JavaScript, I would say most
Yeah,
this day my
yes.
favorite. Haskell, if for production backend, yeah, Haskell.
Okay, that's
A
not
little
bad.
bit
JavaScript,
Rust.
though.
Uh, but everyone is using for front end stuff. So just for like a lot of demo. Of course, script is also used. But Rust, Haskell, yeah.
Yep. Yeah, I don't know. All the complaints that we used to do about the security of JavaScript, and no one listened. Oh well. But anyway, now when you're doing such a calculation, how difficult is it to cycle through sort of potential exchanges like numbers?
Not difficult. I mean, there's we got all the like for all the major languages, we also have libraries. I mean, if you
Hmm.
want to do this kind of a derived key, it's all elliptic curve operations. Just
Exactly. So you're not even doing complex library coding. So now let's just imagine we want to make this a little bit more private. Now, if you and I have a um, sort of ability to update a key, and we can do that, say, through a HMAC process,
mhm,
and I text you something saying this is my my new sort of secret for the HMAC,
mhm,
then you have it, you can calculate it, nobody else can.
yeah.
If you want, you can make it even more complex by doing something like a process on the shared key. The default that I talk about is take the shared key, multiply it by G.
Mhm,
Um, that gives you an ECDSA key that is additive.
yeah.
So we've got the shared key now, the shared secret. Tell me what else I could do.
You can do a lot of encryption. It's any password. Just
Hmm.
anything that's secretive. You can.
Yeah,
I can think of
I could even do a non-secret process that no one will get.
such as.
Um, so I have this secret now with you. What if I now multiply it by the HMAC of your public key plus my public key hashed together and the day of the year?
Mhm,
I've got a totally wacky scheme that even if people know it, they still don't get anything, do they? Because they don't have the secret key. Or I
no.
could use that
Mhm, mhm,
secret as a input to a HMAC to then go Diffie-Hellman exchange part 1, HMAC, HMAC times G.
mhm,
Guess what? You can calculate it easily. You've got these things called libraries.
mhm. Even JavaScript, yeah, you have libraries. So
Exactly. So it's
that's
all
easy.
nice and automated. That's the whole point.
Mhm, mhm,
So on your end, it's completely, utterly automated and easy. Once you've created Scrypt wallet version 42,
mhm,
in whatever way that you want this protocol to exchange, and you've published that, and everyone's using it, then all the fields come out the same, don't they?
Yeah, the same. It's as long as you have the
Same
share
info, same.
secret. Yeah,
Mhm.
secret. What
Yeah.
what are you going to do with secret is
Mhm.
there's unlimited ways I could think of.
Yeah.
Anyway.
So I mean, even if you think about it for a moment, if I do invoice number 1, because it's my first one with you, concatenate the Diffie-Hellman secret that I've just done, do a SHA-256 hash of those two values, multiply that by G. Now, all of the inputs here are public, right?
Yeah, except for the shared secret between you and me. Right?
But that's not an input. That's a calculation. We calculate that based on public information.
Okay. Yeah.
So my public key's out there, everyone knows it. Your public key's out there, everybody knows it. Now, if I decide to have I don't send anything to my public key address, I always use these derived addresses. And I've got lots and lots and lots of them. And I now send something to you on one of those derived addresses. How do I attribute, if I'm a random person on the internet wanting to break your privacy, how do I do that?
I mean, if you reuse, I don't know who you are. There's no relation between your public key and whatever derived public key you have.
Yeah, I'm smart enough not to reuse. So rather, every time we do this, we send to many. What now if I set up a, because these are larger transactions, say we're not talking coffee level anymore, we're talking in the order of hundreds of dollars. What if I split them up into the equivalent of $5 bills?
You can.
By the algorithm, I say secret, invoice number, concatenate 0001, 0002, and I cycle through each of those until I've spent how many number of coins I need to get that value. And I send 1-to-1 to $5 notes to you, the equivalent of $5 notes, I'm saying. So I'm going to send you $100, but instead of sending one transaction with a whole pile of coins being joined, what if I simultaneously send 20 of them?
Yeah, just like a physical cash.
Yeah.
You use $25
exactly.
bill. I think isn't this already at least partially been implemented by hand cash? If I remember.
Partly, yes. So these are some of the things I'm trying to get people to understand, though, and it can be more than just monetary value and the other. So if I want, I can break this up into lots of little tokens. Now, my cost is going to be the balancing factor here, because the 20 transactions independently will cost more than one transaction. But if our cost is in the order of fractions of a cent, maybe you don't care.
No.
Now I can start putting a value on my privacy, can't I?
Yeah, literally. Yeah. Like, yes. If you want more privacy, just pay a little bit more.
If I want to be completely, utterly, insanely private, I could break everything down into 1/10 of a penny.
Okay.
I will sit there sending you 1/10 of penny amounts, like a grandma at Waitrose, and
take all the coins, to the bank, deposit like a bag of coins.
Yep, one of those things. Luckily, the banks have these money things now. They just pour them in.
You can wait. Okay.
Yeah. So, if you start thinking about that gives us a way of doing privacy. Now, one of the arguments is, but then I need to scan everything and find it.
Yeah, right? You can peer-to-peer again.
Again, peer-to-peer. But on top of that, even if you're not available, what happens if I, for instance, have not a cache type address, but now I construct an address that is hierarchical from your public key,
Mm-hmm.
but I put in an alert, and
That,
all you
okay.
do is you monitor that one. So what I now
Okay.
do is I send in the transaction the information you need to find the other transactions, which of
Okay.
course can be algorithmic. It can be a small block of data that I plug into a common algorithm that expands out everything. If you want to
Mm-hmm.
make it nearly infinitely or unboundedly expansive, you could put it into a fractal algorithm, fractal by hash, multiply all that out, more values than I care to think about.
Mm-hmm. Is this in a scenario, for example, maybe Alice sends something to Bob, which
Mm-hmm.
needs interaction, but
Yeah.
whatever reason, Bob is offline at the moment.
Mm-hmm.
So when he gets back, he doesn't have to
Yeah.
scan the whole thing. Somehow
Correct.
it's some kind like almost like an email or some kind of like a
Mm.
buffering. When he gets
Yeah.
online, you
Just
can just
something.
get them.
It could act like a old school pager, for instance.
Okay. Mm-hmm.
You're not old enough, but uh,
I've seen the
30,
movies, but yeah, yeah.
yeah, 30 years
Okay.
ago or so, I used to carry these little things around that would beep
Mm-hmm.
all the time, and make me run out of movies and go answer
Mm-hmm.
phones, and annoying.
Mm-hmm.
Horrible, horrible devices. Now we've replaced those horrible devices with even more horrible devices that not only bingle us a message like text, but
Mm-hmm.
try and call us, try and voice us, try and
Mm-hmm. Video.
video chat. Yeah,
Mm-hmm.
yep. Like I said, horrible things. Um,
Mm-hmm.
not that I go without it anywhere, but
Mm-hmm.
it's still a horrible addiction. Anyway,
Mm-hmm.
so what we can also do, of course, and is set up a different set of addresses that can then record all of the things we're receiving and spending and getting. And potentially we could use that to match all of the other transaction streams that we're getting and have a record of it.
Does this kind of require some kind of like a third-party service, or it sounds like
It could be, but it could just be completely peer related, um, and something that scans for particular address changes or something like this. So it's still doable even without a third party. Depends on how quickly responsive, etc., versus how much I have to go out there and check for transactions and whether one's been spent.
mm-hmm.
I mean, if you think about it now, look at block explorers.
Mm-hmm.
You can watch what happens to addresses as people reuse the same damn thing.
Mm-hmm. Yeah, that's the whole model basically. For
Yep.
any other blockchain, you just get an address and you just input there, and you can see all the history.
Mm-hmm. Yeah. So the alternative that we want to do here is effectively having tree structures, not of these existing types of indeterminate keys, the way that they are now, but ones that are individualized between users exchanging.
Mm-hmm.
So, of course, that can then build into other such things. In the example, of course, what I do is then breaking it up into different accounting functions. For instance, my master key can look at a system that protects my passwords or access keys. That can link to something like a Kerberos, a Cerebos key, depending on how you want to pronounce it. That then provides an access token analogous to either Windows Kerberos for .NET systems or Unix Kerberos for like Linux, Sun, etc. I think there's still Sun out there. Um,
I don't know, maybe
don't know
some
if anyone actually uses it, but um, on top of that, I could use it for salary payments versus interest payments versus anything else. I can pre-calculate amounts for bonds. So as a smart contract, for instance, I can have not the payments, but the potential already signed, not on the blockchain yet because I don't have the input transaction.
Mhm.
And now I'll give you two things you can consider when you're doing this. If you're talking about an anyone can pay type transaction, then there's not really a malleability attack. Because if any input is fine, then someone doing the malleability attack isn't an issue.
No. Mm.
If you think about it for a second, not really an issue. The next part is um, because it's open like that, you have the random payer attack, which there are.
What is that?
Someone comes along and pays your rent for you.
Okay. Why is that
Um,
attack?
Well, I mean, it's an argument that Armory put up to me when I mentioned
Oh,
this
okay.
years ago. I said, why don't you just have it as anyone can pay and just leave it out there and you don't need to have all these things to try and control it? And he said, well, someone could come along and pay it before someone else.
Okay. I
And
mean,
I just
if you,
sat there going, someone randomly comes up and pays my home loan for me. And
I'm happy. Please
someone,
attack me. Please attack. But pay my tax. It's fine.
yeah,
I know.
exactly. Oh, that reminds me, I've got to do mine.
Oh, okay. I mean, maybe America, he already paid you your tax, so you don't know.
Mm,
Attack.
yeah.
Okay.
So, I mean, really, you're going to complain about the random payment attack? I mean, if you want, um, uh, you could argue that, oh no, it's not my money and send it back. But I mean, you got that option depending on what it's worth. Um, so what does that give us? It gives us electronic resource rental. Now let's go back to the old-fashioned type thing that I used to have, like anyone can spend, and let's add lock time and all of this other stuff that were originally touted to be things in Bitcoin that I've mentioned. Now, the argument here is all this stuff could be lost if it's not on chain. Someone could lose all these transactions, right?
Yeah, I think you talked about this before, like many
Yeah.
times. It's the same as
If you
keys,
lose
right?
your key and you
It
lose your
is.
transaction and they're all the same, then you're screwed
Mhm.
either way if you don't have other evidence to prove things. So
Mhm.
move on from that one. It's like saying, if I shoot myself in the head, I might die when I stab myself.
Mhm.
Well,
Mhm.
yeah, it's a bit superfluous. I mean, don't worry about it. Give up.
Mhm.
So electronic resource rental can also link into things like end lock time, because what I can do is I can send you a transaction um, that maybe you pre-sign, or lots of ways of doing it, but I won't go into, like, it could be a two of two where I sign and you sign or something like this. And then what we have is an n-lock timed transaction. And that n-lock time transaction, say a week from now, is valid on the network.
Mhm.
I mean, I can have a video player that watches the blockchain and determines if this key is valid, if this address is valid, I play this movie.
Mhm.
I mean, it can then say, I've got a valid token. Here's the decryption key. That can be distributed over a broadcast encryption system. I watch the movie, but I can only hold it. It's in the item's memory and gets flushed if the blockchain says it's no longer valid.
Mhm.
So that can be automated because I can have an end lock time script sitting, waiting to be sent. And of
Okay.
course, a week from now, I'm the video store. I know this is old fashioned, but Hey,
Mm-hmm.
I used to go to these things before Netflix. Used to actually
Blockbuster. Okay.
yeah, went to that one.
Okay.
And what happens is you get the movie for a week. The end.
Mm-hmm.
There was actually another thing I helped with the deployment and implementation of in Australia. It was called UVI.
Mm-hmm.
You know, UVI is like a movie kiosk.
Okay. I
So
think we still have something like this, like we call it a red box here. Basically, in front of like a Walmart or supermarket,
yep,
it's like a kiosk. You like
yeah,
you can rent a DVD and take it home, $1. I don't know.
yep, yeah, and some of them don't even care that you bring them back.
Oh, because it's too cheap.
What they would do is print the thing.
Okay.
Um, so you could even buy some, or yeah, in theory you're meant to bring it back, but not everyone did. But you could even print that in there. Now, what you can then do is the device can have something that downloads a key, but only while, I mean, which needs to update based on time, etc. But it only works up until a certain date, and that date is mandated by an entry on the blockchain that moves.
Are you talking about the kiosk machine or the home, like a DVD at home, user's
You could
home?
actually do it both ways. You could even then download and print at home, or download and access at home.
Okay.
So if we think about broadcast encryption, one of the extensions that I looked at was using a combination of broadcast encryption, which is the old system that used to be used in satellite TV and cable, and extending it using time. So over time, you need to keep updating keys to stay valid and to retain access.
Mm-hmm.
And of course, you can have an overlap where if you're offline for a little while, it's not an issue. But after a certain amount of time, you lose access.
So basically, you're like a paying subscription, but that
Yeah.
when you renew your keys.
Mm-hmm.
Okay.
Yep. And exactly like you just said there, the subscription could be just a flag on the blockchain, which is spent or unspent. Because
Mm-hmm.
if there's a payment on this address from this address, open. If no payment on this address from that address, closed. Now, if I put the code in the machine to go source address, destination address, and bad guy decides to cheat by sending a transaction to the on address from a different address, what happens?
Nothing.
Nothing, because it's not matching money in the account. It's matching transaction input address, transaction received address.
Mm-hmm.
If they're both correct, good.
Mm.
Internet of Things machines, they can be done this way too. So if you think about that for a moment, we don't need to have all of the complex encryption and controls in our Internet of Things or IIoT, Industrial Internet of Things machines.
Mm-hmm.
They can be set up to verify information in signed transactions.
Mm-hmm.
And they don't even need to do the transaction verification.
Why? Like
Okay, so
SPV?
if I have a signed transaction that is in a block, is it valid and verified, or can it be invalid?
It's of course valid. Otherwise, it will not be mined. Yeah.
Yeah. So if the Internet of Things device monitors the longest chain,
Mm-hmm.
it doesn't even need to do cryptographic operations. It
Yeah.
can say someone else has done this.
Mm-hmm.
Now, the argument will be, oh, but what if I can set up a fake chain and make the Internet of Things devices believe that I'm the longest chain by knocking the network off and DOSing things, etc.
You can, I mean, if I'm writing the software, you can just probe different, again, it's like you probe multiple sources, right, to make sure which one is the longest.
Correct. So I can do that. But on top of that, I don't even need to know what the address of the machine, the Internet of Things machine is. Something I used to do with IDS IPS boxes is you would set them up with a sniffer, but no IP address.
Okay.
So basically what you do is you sit on the wire, like you have a hub rather than a switch, or you put spanning mode on, or etc. And now I just monitor and filter, which I can do at wire speed using XOR filters, certain transaction patterns. If these transaction patterns happen, I care about that transaction. If not, I don't. Now, as an attacker, I generally want to try and send things to your IP address or your domain name or something. If I don't know what I'm sending to, you're just looking for something on this network somewhere, that becomes a bit harder, doesn't it?
Yeah, of course. It's like
So,
IPv4, you can scan all the ports, but if you don't know even the ports are, you just make it harder, much harder.
So what we can also then start looking at are things like password replacement.
Yeah, this one's a big one because current internet, I think for end users, a lot of issues is go to different sites. Each site has a new password. You can't.
Horrible. So one of the things that tried to get brought in the past was PKI, public key infrastructure, and TLS supports, like transaction layer security, like SSL3 supports this concept of client server certificates, where the client has a certificate and the server has a certificate. Now even the problem, of course, sorry?
Okay. Even the client, that will be hard.
It has been in the past, but if you're on Microsoft with the advanced security system for Windows 10 and things like this, and above, like the server, and you're on a domain, then you will actually probably, if you're set up correctly anyway, have a combination of like a PKI, CA and RA server in your organization giving out certificates, and those certificates will be used to sign and send tokens back and forwards between machines for access. Now, nothing stops you from, say, self-enrolling. An example of this would be the use of the self-signed key by in PGP days. Now, you could tell the hard drive, sorry, the computer, the hard drive, the device, this is my key. Does it matter that it's not through a certification authority now?
No, because
not really.
it's kind of the domains already, like somewhere high up in the hierarchy is already certified. So whatever happens below, you can do anything.
And that can be a use for some of the sub sort of master keys. So with my personal smart cardy type key, I can now sign a sub key that signs other transactions. That would then allow me to say, this key is valid accessing this device. And I could sign off on that. And I could then attribute that to my identity key and start building up, this is my phone, I allow access. But remotely, if I lose access to my phone, or it's stolen or something like this, I can revoke access. So as an example, the phone may require access to the internet to validate at least once a day. If you're more paranoid, maybe even more often. It could double check every 8 hours just to have it overlap in time so you don't get caught because you've run out of battery and that it starts up or some silliness like that. But it just keeps going while it's connected to the internet, going, yep, I'm valid, yep, I'm valid, unless you revoke it.
Okay. How does the revoke work? Because if it's some keys are always there, is somehow is expired. How does this usually work? Like for example, like even movie, right? Like a Netflix, like a Blockbuster, I rent some DVD home, and somehow after a while it expires. How does this usually work? Revoke.
So in the old days of PKI, you had what was called a revocation list. Okay. And a revocation list is just a big list of this is no longer valid type certificates for whatever reason.
Okay.
They have been revoked. Now, what will happen is the server will go out and go, is this certificate valid? Yes, no. And if it's valid, keep going. If it's not valid, oops, red, I'm not valid anymore. Okay. That sort of stuff. Now, what you then need to do for users is publish that on the blockchain. Now, your master key could be required to send to your revocation list key. And if you send a message saying revoke Samsung device, then the key associated with the ontological entry for Samsung device, the XML, XBRL, or whatever else you have attributing that thing, now gets put into the ledger as revoked.
Okay.
And when I go out there and check, I now see that this key is no longer recognized. And all I do is go, nope, no good.
So all this like a revocation list, this is maintained, has to be on the blockchain or can be? It's just
it doesn't have to be, but it would be better if it was. So right now, revocation lists, no one really knows whether they're updated correctly, whether things come and go off them, whether someone's attacked them and removed things, when things got added. Whereas on the blockchain, you have this permanent record that you always know.
Okay.
So no worry about people changing the results and diddling things.
I see. And it's small. It's just a list, so that's should not be a problem. Okay.
So next we can look at things like personal device security. Now, right now, what we have is...
Before I can ask, because this password issue has been like a long, big issue for the it's like a major issue, especially for end users. Because how many times you log into some site, you forget a password, and then you have to reset everything, and you have like 100 sites. So because even for me,
and
for where
the alternative is you trust say Facebook and Google, because they would never steal your passwords. Anyway.
But here's the thing, because even for when I'm using BSV powered apps, I can feel like if I just log into let's say money button, I can just swipe. There's no password. I just kind of like do the signature, right? Then you can know that's me. But why do you think the current internet has not moved to me? It seems like a better, more secure version of granting access to authenticating to the server. Why is still mostly it's still password based versus this kind of just network effect?
Unfortunately, people got used to it, and we ended up stuck with it because there isn't anything that is like 10 times better.
Okay.
The password managers are hard. The need to manage keys is hard. All these things are hard, so users don't end up doing them.
Can you imagine this if you use some kind of a key derivation or management scheme? It can be, if somebody just built a better app, let's say I don't know, I wouldn't call it a password manager, like a key manager. So you can just log into all the different sites, just swipe, just verify. Then there's no password even transfer or even hash of it.
Yeah, that would be even perfect. Like you could extend that by again using a tokenized access, like Kerberos or Kerberos. There's actually two different pronunciations because the three-headed dog is actually the correct term, but for some reason, Cerebos with a K and Kerberos and everything like all derived from the same thing. But anyway, that's a side thing.
Do you see this? Do you see this in the long term is going to be 10 times better, and then the regular user is going to migrate to more secure version?
I definitely think it could be, yes.
Okay.
If someone built that correctly, which takes into the next bit I was actually looking at, which would be things like personal device security. Now, rather than just accessing your files, one of the benefits you can do is derive a number of keys. So when we were talking before with the process of creating a variety of different keys, like with different invoice numbers, etc. What I could also do is the hash of a file, or some file identification, or the sector ID, or anything else I want to build. Now, if I take the sector ID, concatenate with secret, I can make a secret. Or I can even take the hash of it if I wanted a bit more randomization. Now, what that then allows me to do is encrypt the file using that information. And then, although you have an algorithmically derivable system, if done right, can be secure, like every single file, every single sector, whatever you want to incorporate, has its own encryption password.
That's all derived.
Yeah. So imagine each individual sector on your phone or your hard drive has its own sort of derivable sort of encryption key. So it doesn't even need to be at the file level. It can be right down to the sector level, and the sector itself gets encrypted.
Okay, I would say that maybe that's a little bit paranoid, but definitely you can do that.
Oh, there's plenty of people who are that paranoid out there, but you could actually create it so that it's that sort of secure. You could then have a YubiKey or a smart card that holds the master key. You could have a backup of those if you needed to in a safe deposit box in a different country. Who knows? All sorts of fun, funky things you could do. So then that enables you to have maybe even like your mobile phone could be an authentication device for your laptop. And between them, they negotiate how you decrypt and start up. And done correctly, that could even be fairly fast because if you're now calculating a whole lot of values that you XOR in the future, that could be done just about at wire speed. I'm not saying it would be right now, but
okay. But all in this case, either it's my laptop or my phone. So my master key would not be on this, right? It's like this is almost like a hotkey kind of thing. So I always keep my code storage somewhere else, like a smart card or I don't know, lockbox. Okay.
Yeah, you can have the little YubiKey things. I've got one somewhere. I've got piles of the damn silly things, like these things.
Okay.
Somewhere I've got a probably one of the computers. I got one of the little ones around too. Too many of the damn things. Because the little one I need for my phone because it doesn't have the bigger USB. But so you can incorporate all of these devices that now enable you to control how your system's encrypted or not.
So,
Potentially, you could then say unencrypt this drive, but not that one. So
this seems to be putting like if we do it this way, I think it's now we have almost like a root key, like a root master key. So this has to be super secure. Otherwise, if this gets compromised, all your devices, all your like website access, it's all compromised. So I bet there's some like I don't know the threshold or I don't know secret share. It has to be to make this ultra secure.
except we got this scriptable language stuff here in Bitcoin world that allows us to do things like multi-key. We can have a multi-signature type scenario. So in theory, I could say X, Y, or Z, or X, Y, and Z, or X or Y plus Z, or any other way I want to make it. So remember, you can also do sort of multi-party sort of, which don't think we get time tonight, but remind me and I'll go over this. So one of the things I solved that isn't in Diffie-Hellman is we have a way of doing a multi-party sort of Diffie-Hellman exchange for multiple numbers of people that is secure. So instead of Diffie-Hellman between you and I, we can do it between 3 people, 4 people, 5 people. If you want to make really complex code, 500 people.
Okay. Yeah, they do this kind of like a trusted setup. I don't know, for Zcash or something. I don't know, for all this kind of so-called privacy coins. Yeah.
Yeah. None of which I'd trust. Yeah, trust me, I've deleted the information from my hard drive and blah, blah, blah. Yeah, right. I trust you. Yeah. Yes. Anyway, so what we can, of course, do is have more keys, more requirements, and more complexity if we want. So, as I said, only 5 minutes to go, but so I won't do it this time. But next time we'll have a bit of a dive into how we can do Diffie-Hellman with 2 of 3, 3 of 3, and other such things. Also, remember, part of the 479 type stuff, the threshold things, is that allows us to have our master key protected.
Yeah, that seems to be very important because now the master key is really the master. Because that's get compromised, all your digital life pretty much get compromised.
Yeah. So what we can do, of course, is we can have multiple components such as keys on smart cards that enable us to do threshold updates, etc. And we can have those connected to other devices that we can isolate from time to time, and other devices that we can recalculate. So we can go through this process of enrolling my device and letting it trust certain other things, and we can even automate all of that. And once you start automating all of this and integrating the updates, then it makes people's lives a lot simpler, especially than passwords. Now, the secret's going to be getting it done correctly. I mean, there are good and bad smart cards, for instance. There are smart cards that are really difficult, even if you get physical access, to copy. I mean, there's no such thing as an impossible system. In theory, there are all these so-called attacks against secured hardware, but I can't remember the name of it. There was a little Linux device, for instance, that was in a sealed case and tamper resistant, and you couldn't do anything, or the drive would erase, not just like format the hard drive, but properly erase it to all zeros. And it did that quickly by erasing the keys in a section of the hard drive, and once they're gone, the rest is permanently encrypted. But even that has some attack vectors. They're just ridiculously expensive and difficult. Like you take it to negative 200 plus Kelvin, and then remove bits, and then using a SEM, a scanning electron microscope, you work out the positions.
Okay, that sounds like a paths. In the worst case, you can even replicate all the atoms if you want, but just
exactly. I mean, you sit
too
there
expensive.
Exactly. I mean, IBM talks about how they can make little logos saying IBM at the atomic level. And if you want to pay for that, then go for it. But if you think about how many atoms there are per millimeter, you've got a long, busy job.
To steal $5, I think. Yeah, again.
Oh, no.
Yeah, you can if you want, but you probably nobody. I mean, you can in theory do it. Okay.
All right. So that should cover now and give you some other ideas. But next week we'll continue this in going into Diffie-Hellman exchanges in multi-party, which is something that Mr. Diffie and Mr. Hellman didn't invent. So sorry. It's actually simpler than people think, but I'll detail all of that next week. It's one of the concepts we've got. So
yeah, that's some okay, something to look forward to, because if these two people didn't figure it out, probably something worse patterned.
Well, the difference is the processes behind sort of how encryption was done in the past and how it can be done after Bitcoin are different. Bitcoin flipped many things on its head. So many of the attack vectors are different. The Sony key attack doesn't work on my version of how you use things. If you never reuse your signing key, or then there isn't an attack. If you think about it for a moment, what they're talking about is, if I can get this version of K and this version of K, I can work out the distance between them, even if they're the same number, it's even easier. Then I can do an attack to calculate the actual private key. But that requires that you have two different signatures that you can analyze using the same key. But if you don't ever get two signatures from the same key, then you don't have that.
No attack.
So you even remove that if you've screwed up and you don't have a randomized K.
I see. Yeah. Different paradigm. That's something worth listening to. Okay. All right. Look forward to it next week then. Okay.
No problem. Okay.
Okay. Enjoy the rest of the day. Okay. Talk to you next week.
Bye.
Okay. Bye-bye.